Okay, everyone, today we are going to get a little bit theoretical and we are going to be talking about the concept of infinity. So, in the last couple sections, we've looked at compound interest and how that works and what it looks like in the real world. Now we are going to see how far we can push it as we look at continuous compounding. But to do that, we need to look at the concept of infinity. So infinity is not a number. The reason it's not a number is because it's infinite. I know I'm using it to describe itself, and you're not really supposed to do that, but it's hard to wrap your head around. So the reason it's not a number is because the way numbers work, if you came up with some number for infinity, I would just add one. I would say I've got infinity plus one, and then all of a sudden I would have a new infinity. And then you could go back and add one again, and you would have the new infinity now. So we can never actually put down a number that is infinity. It's just the concept of forever. And that's hard to deal with because our brains are just, quite simply put, not set up to deal with things like that. We are very good at discrete values, especially small discrete values. You can notice the people in a crowd, whether it's a couple dozen or it's a few thousand. You can know how many chips are in your bag of chips. It's a number that you can look at. When we start talking about things like infinity, the number just gets so huge that it actually blows your mind. Um, and especially because infinity does not always work the way you would expect, which is a little bit of a preview for some of the stuff that we are going to come across later. And to illustrate this concept, I want to just give you a little thought experiment here. We'll walk ourselves through it and show you how infinity acts a little bit weird sometimes. So imagine you get in your car and you want to drive 2 miles. You're just going to go straight down the highway for 2 miles. No big deal. It's something that you've done before. But let's think about breaking up that 2 miles into halves. So to go halfway there, you go 1 mile, and fine, you got another mile to go. But then you go another half, so that's a half mile. And then you go another half, so that's a quarter mile. And then you go another half, so that's an eighth of a mile. And you go another half, so that's a 16th of a mile, and so on and so on and so on. And your halves just keep getting smaller and smaller and smaller. And we've got infinitely many of them. We can keep taking half of the previous number. But you can drive 2 miles. You've done it before, I'm sure. If you've driven a car, you've probably driven 2 straight miles before, right up Highway 51. So we know the answer. We added up infinitely many numbers: 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so on, all the way to infinity. But our answer is a real number. It's 2 miles. So infinity doesn't always act the way you expect. And we're going to get into a little bit of calculus. Don't freak out though. We're not going to dive deep, but there's a concept in calculus called limits that allow us to explain behavior at infinity. And that's what we're going to use just very shallowly, but we're going to look at the limit as x approaches infinity of certain functions. So remember from Algebra 1 that a function is some equation or some rule that you put in a value and you get out a value. So we're talking about real number functions here. And so we put in an x value and we get out a y value. We could graph it if we wanted to go back to Algebra 1, not a big deal at all. But what we're going to do is we are going to see what happens as that x value gets towards infinity. So it gets infinitely large. So let's look at our first function. We've got f of x equals 1 to the x power. So let's find this limit as x approaches infinity. So to do that, let's just check some values and see if we can figure out what's happening. So 1 to the first power is 1. 1 to the 10th power is also 1. So remember that if you take something to a power, you are just multiplying it by itself that many times. So we're going 1 times 1 times 1 times 1 times 1, 10 times, but we still get 1. 1 to the 100th power is still 1. So no matter how many times we multiply 1 together, we get 1. The output, the f of x, the y value, it is always 1, no matter how big our exponent gets. So what we can say is that the limit as x approaches infinity of this function is equal to 1. In fact, it's just not a very interesting function. No matter what we do to that x, our answer is always 1. So let's look at one that's a little bit different than that. Our next function is going to be 2 to the x power. So we still have that variable up in the exponent, but now the base, the thing that we are multiplying by itself over and over again, is not 1, it's 2. So we're going to do the same thing. We're going to look at some values and we are going to see if we can figure out what's happening as x gets really, really big. So let's notice here. If we've got g of 1, so that's just saying that we're going to replace that x with a 1, we get 2 to the first power, which is 2. G of 2 is 2 to the second power, which is 4. G of 3 gets us an 8. G of 4 gets us a 16. And we keep going. We get 32, we get 64, we get 128. And it just keeps getting larger and larger. So as x gets larger, the function is increasing without any kind of bound on it. There is no upper limit. This is known as a divergent limit because it's going to infinity. If I keep increasing x, then my g of x, my y value, keeps getting larger, bigger and bigger and bigger, and it is never going to stop. So this is actually true of any function with a base larger than 1. So remember when our base was 1, all we got out was 1. But if our base gets bigger than 1, then we're going to go to infinity. So even if it's something like 1.1 or 1.01, we are going to go to infinity. It's going to go slower, like more slowly if our base is smaller, but eventually we are tending towards infinity because the next number is always bigger. And I'm sorry about the train if you can hear that. Okay, let's look at one final function here. Let's look at h of x, and this time our x is in the denominator. So we're not dealing with an exponential function. We are going to deal with just this is known as a rational function. So once more, let's find out where this function goes as x approaches infinity. So let's plug in some small values. H of 1 is 1 over 1, which is the same as 1. H of 2 gets us 1/2, which is the same as 0.5. H of 4 gets us 1/4, which is the same as 0.25. Then we get 0.125. So notice this is actually the same thing as our highway problem. We are just cutting everything in half over and over again. But let's get even bigger. Let's say that h of 10 is 1/10, that's 0.1. H of 100 is 1 over 100, that's 0.01. H of 1000 is 1 over 1000, that is 0.001. As x gets bigger and bigger, the function gets closer and closer to 0. There's less and less value there. In fact, as we go to infinity, we may as well call it 0. This is so close to 0 that it may as well just be 0. We can't call it anything else. So we would say that the limit as x approaches infinity of this function is 0. So this is going to come up here in a minute because we're going to look at a theoretical bank, and they are a very generous bank. So we're going to use our knowledge of limits that we just picked up, and we're going to see if we can figure something out. So far, we've looked at this compound interest formula, and we've looked at yearly compounding, quarterly, monthly, weekly, daily, all totally normal things to compound. But there's no reason this formula can't be used to compound at even faster rates. Maybe we want to compound hourly. Maybe we want to compound every minute. Maybe we want to compound every second, every less than a second, as many times as we want. So here's the deal. A bank is going to come up to you and they're going to ask you to invest $1 with them for 1 year. But they're going to use an infinitely small unit of time to compound interest. So smaller than a second, smaller than a fraction of a second. Whatever the smallest number you can think of, it is smaller than that. And every that number of seconds, every small time there, they're going to compound your interest again. So essentially you could say that your compound or your interest is compounding continuously. It never stops compounding, just goes on forever and ever. So here's the question. After 1 year compounding continuously, how much money is going to be in your account? Sorry about the dog there. Okay, let's start with some larger units of time and see if we can't figure out a way that this works. Dog is very excited right now. Okay, we've got our 100% interest, so that means that the rate here in our compound interest formula is going to be just 1. So if we take this and figure it out with compounding once a year, we end up with $2. If we compound quarterly, so 4 times a year, we end up with $2.44. If we compound this monthly, so we use an N of 12, we end up with $2.61. And finally, if we compound daily here, so we end up with 1 plus 1 over 365, all to the 365 power, we end up with $2.71. So does this go against what your intuition told you? Did you think maybe that this continuous compounding was going to get you an infinite amount of money? It's a little bit weird, and this is why I mentioned the 2 mile thing at the start, because we are taking in our number of compounds a year. We are taking that all the way up to infinity, but our bank account balance is not going to infinity. It's going to go to an actual number, and that number is going to be $2.72. So in our first one over here, we are compounding hourly. So this is how many hours are in a year, 8,760. And our bank account balance after that is $2.72. In the middle one, we are compounding every minute. So there are 525,600 minutes in a year. And if we compound once a minute, our bank account balance is $2.72. Finally, what if we want to compound once a second? So there are 31,536,000 seconds in a year. And if we use that for our N, we get $2.72. It's never going to go above that $2.72. So the number that we have just discovered is known as E. And it is taken by, or one of the definitions of it is to take the limit as this n, this bottom number, and also this exponent go to infinity. So let's look at why this might be happening by looking at some of our other things that we figured out earlier. So we knew that 1 to the x power was 1. And we also noticed earlier that if we take 1 over x, as that x gets bigger and bigger, that becomes 0. So essentially this inside of the parentheses is 1, but it's not. It's actually really, really close to 1, but it's not exactly 1. It's just a little bit bigger. So we would expect it to go to infinity. If we take this exponent all the way up to infinity, we would expect a divergent outcome here. Our limit would go up. But as this exponent is getting bigger, this is also getting closer to 1 because this 1 over n is getting smaller and smaller. So this is getting smaller and smaller. The exponent is getting bigger and bigger, and they're kind of fighting with each other. And there's not going to be a winner. If this 1 was the winner, then the answer would be 1, and if this exponent was the winner, then the answer would be infinity. But there's a little bit of a stalemate, and the stalemate happens at around $2.72, or E. It's a number just like pi, where it's an irrational number. It goes on and on forever, but there's an infinite decimal there. So there are the first few digits of E right there. And this is what you could think of as the upper limit of greed. So no matter how greedy I get with my continuous compounding, I am never going to get above this E number. It's the max. So let's use that to come up with a formula. And this formula is actually easier than the compound interest formula. The problem is it's not anything that happens in real life. It's really theoretical. So in our last example, the interest rate was 100%. You're never going to get an interest rate of 100%. So let's derive a formula that allows us to use any interest rate we choose. So we're going to go back to our compound interest formula, and we are going to say that our B is our balance equal to the principal times that quantity 1 plus the rate as a decimal over n, all to the n power. And we're going to take the limit of that as n goes to infinity. And it's going to get us this. It's PERT. So our balance is going to be equal to P times E to the exponent of R times T. I threw a T in there also because maybe our bank account is going for more than 1 year. Maybe we've got a 3 or 4 year investment here. So we need to be able to multiply it by the number of years. So P times E to the R times T power is going to be our continuous compounding formula. And you can find the E button if you have a scientific or a graphing calculator. It's on there. If you use the calculator on Google, then there's an E there if you go to scientific mode. If you are using like your iPhone or your Android phone and you turn your calculator sideways, then one of the buttons there will be E. That's where you'd also find things like pi. So that's where you would find it, and you want to take the exponent of that. So this doesn't actually exist. No bank is going to give you continuously compounding interest, but this is, like I mentioned, a theoretical maximum. We are never going to get above this amount of interest. So if you are doing some calculations and you find a number that seems like it's going to be above that amount, you need to go back because you probably did something incorrectly when you were punching something into your calculator. So here's one example. Just try it yourself. Craig deposits $5,000 continuously at 1.12% for 4 years. So what is Craig's ending balance to the nearest cent? Okay, so in your calculator, you should have gone 5,000 times E to the 0.012 times 4, all in the exponent there. And Craig's balance after 4 years is going to be about $5,245.85. So if you didn't get that, $5,245.85, maybe go back and look at your calculator work again or ask me in class, and we'll see if we can't figure that out. All right, that's all I've got. This was a long video, I know, but it's had some interesting concepts in it, hopefully. So bring me any questions, anything that confused you, and I will see you tomorrow.